Thank you. So I'm going to talk about instrument development happening at NASA Goddard Space Flight Center right now. It's Swath-Mapping Lidar for application to lunar science and exploration. So I'm the one presenting, and I've been working on this concept with colleagues at Goddard for a couple of years. But I also want to acknowledge, obviously, the engineers, Guan Yang, Jeff Chen, Hui Li, and Charlie Sun, and Dan Kremens in particular, who have been, really the brains behind the technology approach. So the first question, is why do we want to keep developing Goddard lidars? And the answer is that Goddard is a long storied history of making first in terms of measurements at Mars, Mercury, the Moon, for creating foundational data sets that have been useful to many parts of science, and also now for Artemis are playing an important role in getting the information we need to design those systems. They're really well known for their ranging accuracy, the geodetic control, and the uniformity of the measurements. That means that whether it's day, night, permanent shadow, you get the same measurement quality, and there is no bias that way or difficulty in using those data sets. However, a challenge of LiDARs have been that they are active instruments and so are sometimes limited by instrument power. And can I get a screen back? And so the challenge has always been for LiDARs, the instrument footprint size, how many footprints you can put in a second, and the resulting sampling and coverage of the surface. So they provide great geodetic control, but to this day, it's nice to combine them with images to be able to get no gaps. And so we have found a new technology can actually achieve a full sampling and we think higher data quality. And also in the clock stack report that was mentioned several times this week, LiDARs continue to play an important role in the type of measurements we want to get from future orbiters. So our goal is to really radically advance space LiDAR technology applied to planetary science and lunar science. You can see here an image that shows a comparison between the sort of spot size and spot spacing that have been obtained for several LiDARs of the past couple decades. You can see that generally the spots have gotten smaller from MOLA to MLA to LOLA, and denser in a way with less inter-spot spacing between them. But those are still very, very sparse. And so on the right, I guess something disappeared. There should be basically a long rectangle that is entirely red under swath mapping, where we will get 100 to 200 meter wide swath that is completely mapped at the same sub-meter resolution along track and cross track. And so that means that we'll get more than 1 million measurements per second compared to about from a dozen to 100 for current technology. And so you can see on the sort of zoom images on the right there that that will afford a much better data set for anything to do with science and technology, for hazard detection and mission planning also on the surface. And so we think we have a technology that can achieve that. I'm going to go very quickly through the science questions that are driving this. We think meter scale is important to understand polar volatiles and cold traps. There's been talk about micro-cold traps, and the meter scale is important to know like what could be sampled by astronauts and such. We also think that it can really push forward the knowledge of the lunar interior by better mapping deformation due to the tides at multiple length scales and time scales. Also understanding distant volcanism, small features basically of tectonic activity and volcanism, recent impacts. All of those typically rely on stereo DMs, but there's a trade between stereo quality and albedo changes, and so the LiDAR would be a very nice supporting data set for a lot of those studies. So here on the right, you see the full traceability matrix we've derived for this type of a measurement. And on the left, you can see just a little slice of it that shows you that, with meter scale topography and meter scale albedo as well, normal albedo at 0 phase, we think we can achieve and respond to a lot of those, community documents that we've seen and talked about this week, including Decadal, Artemis 3 SDT, and the League type of documents. And so one important thing is to get contiguous spots with similar type of elevation precision, repeat observation, and normal albedo. So as I mentioned at Goddard, we've continued to try to push the boundary of LiDARs. And in particular, this Goddard has supported under its Radical Innovation Initiative, a new technology that we call Casas. There's a paper from last year that describes that in a little bit more detail. There's also been Earth science support for this through ACT and IIP. But the moon is actually a much easier target than the Earth for applying this measurement approach. And so I'm going to show that in a second. And that's primarily due to the fact that we have much lower orbiting altitude. We don't have clouds, so there's no cloud folding issue in the LiDAR processing. And so, we think there's a pretty clear path to flight on a timescale that can match Artemis observation needs. Also, there is a poster 36 about Jeff Chen that talks about applying the similar technology to EDR. So what are the key components to enable this measurement concept? First is a wavelength tunable seed laser. And with the gratings, we can actually convert a wavelength change into a beam direction change. So that means we can do non-mechanical, very high speed steering of the laser beam. So with a single laser, we can actually map hundreds of locations cross-track. And as we advance with the spacecraft speed, if we can do that fast enough, then we can also get contiguous measurements along track as well. And so that relies on very efficient design. And so that's why we have a linear mode photon counting detector array that is more than 90% efficient in quantum efficiency. So here's the sort of notional block diagram. You can see at the bottom here that we have, I can't see the laser pointer, but sort of that seed laser, that the wavelength tunable, a fiber amplifier to get us to the kind of energies we need. We stream basically series of pulses that change slightly wavelength. And as they go through the grading, that transfers into a cross-rack position that is imaged back onto the detector. And so there's also grading on the receive end. And the grading is actually a critical part of that because they achieve non-mechanical beam steering, but also on the backside, they enable you to reject most of the solar background and to get to that super efficiency. Each shot, we will only get about a dozen photons back, and we need to make that 10-minute measurement. So it's a very, very efficient design where we can get several orders of magnitude more pulses for about the same amount of power as LoRa. So this idea was developed through the IRAD program, as I mentioned, at Goddard for a couple of years, and demonstrated last year on a rooftop to distances of about 1 kilometer. And that was sufficient to demonstrate the general approach, generate that beam steering cross-track, and importantly, verify the link computations. So we can apply that now to orbital distances and different targets. So now there is some efforts to develop the components needed for the Earth applications. So those components do not exist yet. Very high peak power required, different type of wavelength to apply to Earth. But for the moon, actually, those components are reachable and nearly available. So we've conducted also instrument design lab studies at Goddard to better understand how the instrument at the moon would work, how to bring it to flight, the sort of challenges, and notionally what we should focus on. And so we've applied that to a DALI proposal we submitted recently at 1550 nanometer to basically achieve what I was talking about, contiguous swath mapping of the moon, focused on the pole potentially, but really for global targeting as well. So thank you. And if you have any questions, I'll be happy to take some.
So I think we have time for one quick question.
Yeah, really, really nice talk. So again, how many wavelengths are you looking at in the 1550 nanometer region?
Yeah, so 1550 nanometers. So yeah, sorry, I didn't mention the range of wavelength. So it's pretty narrow range. So typically it's plus or minus 7 nanometers around that. So we scan a pretty narrow range, but we can do about 1,000 different wavelengths or colors within that range. So for the design on the moon, we're thinking only about 100 to 200 to minimize the the requirements on the components. But you could extend that to 1,000 colors if you had either several detectors or like more efficient receivers. Yeah.
Thank you.